Good day, and welcome to this presentation of electrical engineering and how to establish a practical engineering program without breaking the bank. Over the past decade, I've read numerous government reports indicating that there are serious labor shortages in the field of electrical and computer engineering, and these skill shortages have become a pressing issue for major global economies such as the United States, the UK, and China, just to name a few. But why do we have so many nations that do not have enough engineers to meet the demands of these critical sectors? And what is the educational industry doing to address these needs? Well, most will say that ramping up of STEM education will do the trick. But is this really what's happening in reality? Regrettably, based on my observation, it's not. Over the past 10 years, I've consulted with numerous schools all over China and abroad. And what have I seen? Electrical and computer engineering is entirely absent from everyone's actions plans. And part of this problem is based on the findings of numerous educational reports, which have indicated that electrical engineering is the most expensive program that schools can offer. And this fact alone would be enough to discourage and dissuade most administrators to support the development of said programs. In fact, electrical engineering is second only to the sciences, where courses such as math and English usually come in as the cheapest according to these reports. Moreover, as there is a lack of professionals in these sectors to begin with, there's also a lack of professionals, be it from industry or from the educational sector, that are qualified to teach engineering without additional training. But what about teachers who might be interested in learning? Well, based on the discussions that I've had with professional educators, most of them indicate that there's a lack of support and materials needed to implement changes to the curriculum. And this phenomenon is not unique to engineering. In fact, it's almost universal across all subject areas. And finally, in my discussion with teachers, I found that many of them feel that the idea of electrical engineering is just too difficult and are hesitant to even try implementing a practical engineering program, even if the materials were made available to them. So this presents a major obstacle for society as large, as there seems to be no viable way forward. But that doesn't need to be the case. As such, I've spent countless hours over the years assessing the obstacles and finding ways to implement electrical and computer engineering into the curricula. And what have I discovered? If it's done properly, a practical engineering program can be done just as economically as the average math or English class. And this means that a practical engineering program is a viable possibility for most high schools. And that's what I'm going to show you today. So as I indicated earlier, electrical engineering is the main focus of today's presentation. And I'd like to start by sharing this report from the United Kingdom, which indicates numerous skill shortages in critical sectors to the economy. Now, the ones I've highlighted in yellow are all related to computer and electrical engineering. But it's not just the United Kingdom which has serious shortages. In fact, most developed nations are facing these same challenges. And this is actually kind of surprising to me because when you look at the IGCSE physics curriculum, there's a large section on electromagnetism in the curriculum. And electronics is also covered in the design technology curriculum as well. And there's even an IGCSE course called electronics. But unfortunately, many of these courses tend to approach electronics from a theoretical standpoint only, and they do not actually get into the applied application of the theory, which is what we really need to focus on, if we're going to address the global skill shortages in the critical sectors to the economy. So what we really need to do is find a way to keep the costs down while still providing students with meaningful learning opportunities. Well, there's different methods that teachers can use to teach electronic and electrical engineering, which I'm going to be elaborating on in just a moment. And each of these approaches has its own strengths and weaknesses. But you might be surprised to know that the most expensive options out there actually have the lowest impact on teaching and learning. In contrast, the cheapest options has the greatest measurable impact towards developing the desired learning outcomes, while also laying the foundation for the development of other skills such as CAD down the line, which I'll talk about later in this presentation. However, the hardest thing for us as educators is to design projects that are aligned to specific learning outcomes rather than just focusing on the project itself. And this has been a major issue that organizations such as the World Economic Forum has identified as a major shortcoming in many STEM products and curricula. Regrettably, we can't really rely on companies to solve this problem for us. And this is because corporate interests generally focus on marketable products that are easy to implement and can make the company as much money as possible rather than focusing on higher learning outcomes. Therefore, we as educators need to work together to lead the change that we want to see in education for ourselves. So what do you need to start teaching a practical engineering skills in your class? Well, there's a few different solutions out there that you can use. We can look at do-it-yourself kits, breadboards, which are pretty common in a lot of computer science classes, prototype boards, and printed circuit boards. And in just a moment, I'm going to talk about the strengths and weaknesses of each of these methods. Now, if you're unfamiliar with any of these approaches to implementing electronics, do-it-yourself kits or PCB boards look like this. The circuits are pre-designed and all the parts you need come with it. Therefore, students only need to assemble the circuit themselves. Prototype boards are basically a blank slate, which allows the designer to create any circuit they could possibly imagine. And breadboards are basically the same idea as prototype boards, but we have the ability to rewire and reuse parts. So we could modify the design or reuse parts as necessary. Now, do-it-yourself circuit boards are popular resources that schools use as they try to develop an electrical engineering program for the first time. They are quickly assembled, which is a bonus for a lot of people. However, there's limited customization. Actually, in reality, there is no customization that the students can make. The circuit is pre-designed and you can only assemble it one way. They also don't come with replacement parts, so if a student loses a part, damages a part, or inserts a part incorrectly, well, you're kind of tough out of luck. You basically need to throw away that circuit and start all over again with a new kit. And there's also a lack of scaffolding. There's no way to really differentiate this project to make it easier or more difficult based on your students' needs. So from an educational standpoint, these are not actually all that good because there's no scaffolding, there's no differentiation, and there's no way for students to customize the designs. And realistically, they're not really learning how or why the circuit works. They're just assembling the circuit and they don't really have to give it much thought. So I want to refer to an idea from Arthur C. Clarke. Any sufficiently advanced technology is indistinguishable from magic. Now, a lot of do-it-yourself kits and circuit designs like this are actually quite advanced, but the students don't understand how or why they actually work. They just understand what it's doing, but they don't understand how the circuit actually operates. So from this standpoint, the project is basically just magic to them. But we want to help our students move beyond rudimentary knowledge of what something does and start developing the deeper understandings of how and why things work in the real world. So the next option is breadboards, and this is a commonly used approach to teaching electronics and electrical engineering in more advanced programs. Now you might think that I'm going to recommend this approach since it's commonly used, but you might be surprised to know that this is not my preferred method of instruction, and I'll get into why that is in just a moment. Now, one of the biggest problems with breadboards is how confusing the wiring is. And you can really see this, even in a simple circuit design like this. We have all the wires going all over the place. It's like a complex labyrinth that you have to navigate. And this makes it very difficult for students to figure out what's happening and why. And this is because the connections are very abstract. We don't really have a nice clean connection between the power to a component and then to the grounding point. Now, we do technically have the ability to reuse parts in this example, but what tends to happen is that the parts just tend to get thrown away as it takes too long to sort and organize them. So although the parts are technically reusable, in reality, they don't get reused. And breadboards also lack permanence. Now, this isn't necessarily an issue per se, but I really like to have projects that students can take home and show their parents. And with the idea of breadboards being reusable, they can't really do that. So my final thought about breadboards is really well represented by this quote from Leonardo da Vinci. Simplicity is the ultimate sophistication. Now we can simplify breadboards by taking the time to simplify our circuit like what we see in this example, but even with all the time and effort that's gone into simplifying it, the connections are still quite abstract. Now for me, I can follow the circuit. However, for a student who's just learning electronics for the first time, this can be quite difficult. So there's another method that I find far more beneficial for students to use when learning electronics for the first time, and that's the prototype board method, which I'm going to show you on the next slide. Here I'm showing you three identical representations of the same circuit. On the left, I've created a USB cell phone charger using a breadboard, and I have that same circuit on the right as a prototype board. And then I have the electrical schematics for both shown on the bottom left-hand corner. Now, which one of these circuits do you think is easier to understand, and why? And I'll give you a moment to think about that before you respond. So with the example on the right, you can easily see the logical connections between the different components. And this circuit layout looks almost identical to the electrical schematic. So it's incredibly easy to see how the parts interconnected with one another and to compare the physical circuit board layout with the electrical schematic. And this makes it much easier for students to visualize and understand a circuit as they start learning electronics for the very first time. Moreover, as a teacher, this is representative of best practices in education. We always want to find ways to simplify things, make it as easy as possible for our students to understand and learn while understanding complex topics. Because our students already have so many things that they need to worry about already. So the last thing that they need to worry about is added complexity where it's not necessary. And this brings us to the benefits of using prototype boards when teaching absolute beginners. So the first thing I want to talk about is this idea of modular circuits, creating experimental circuits that will provide you with the ability to rapid prototype new designs quickly and easily. So this is an example of a standard electronics kit that you can buy, and it's not overly expensive, and it allows you to do a number of circuit experiments with minimal prep. However, I'm not a big fan of these pre-made circuit kits as they have limited options beyond the initial experiments. And what I really want to be able to achieve long term is to get our students beyond these initial experiments and start designing their own experiments. Therefore, rather than using a store-bought kit like this, I like to get the students to build their own modular circuits and then use those circuit boards to build their own experiments. So now I'm going to show you what a student-made modular circuit experiment would look like instead. Now, a modular circuit project like this provides a number of advantages which may not be immediately evident, and they may actually save you a lot of time down the line. As for myself, I always do this project in a foundations course, but I will often jump straight into simple circuits in more advanced course offerings. Regardless of the approach that you use, it's important to always provide a supportive and scaffolded approach to this kind of project-based learning so that your students are given the opportunity to develop the skills that they need to succeed. As for the advantages of doing modular circuit board projects like this, opposed to skipping this type of project completely or using pre-made commercial kits, well, the act of building these modular circuits will expose the students to the idea of building a prototype board on their own, which will help them down the line. Secondly, this is more important in my opinion. By building these modular circuits, students are given the opportunity to develop the tactile skills that they will need to design, build, and test more advanced circuits in the future. This creates a safe learning environment where skills become cumulative and has countless advantages to teaching and learning. Moreover, by developing a logical sequence where one's lessons lead into another, students only need to focus on one big idea at a time. But more importantly, students will begin to see how advanced concepts are interconnected, and this will help them see the relevance of what they're learning and why. That being said, one of the biggest problems with electrical engineering in most cases is that the minimum point of entry is typically quite high. So it's important for educators to break things down into more manageable chunks so that we can make the learning curve much more gradual for our students. Therefore, with a modular circuit experiment like this, students only need to focus on how to build a simple circuit board. And although this may seem simple, it's actually a lot more complicated than it sounds. For instance, you'll find that there will be a number of students who will try to take shortcuts when doing a project like this, such as not properly measuring a wire or not properly stripping the insulation. And this often results in a circuit that will not work. And that's to be expected. But with simple circuits like this, students can easily see their mistakes and how it impacts their experiments when they get into the big group project. And this process of learning from one's own mistakes is important as you don't want the students trying to attempt more complicated designs without first having the prerequisite skills that they need. This includes having the theory necessary to design a circuit, but also the practical skills necessary to build and test it. Now, once we have a number of modular circuits, we can start using them to conduct various design challenges which will become increasingly more complex. So give your students a series of electrical schematics, and then have them try to figure out how to build each circuit using the components that they have available to them. Moreover, each challenge should have the students compare and contrast different part configurations to help them understand the finer nuances of each component. For example, in the first experiment, students would need to determine if the direction that the LED is installed makes a difference, whereas experiment 2 would have the students compare and contrast the difference between an SPST switch and a push switch, and so on. Furthermore, students would also develop a number of visual literacy skills as they learn how to read an electrical schematic and translate that into a physical circuit design. And using their modular circuit boards, their final experiment might look something like this. In this example, students would have to connect multiple modular circuit boards to create a more complicated circuit design. So here's a short video of students using these modular circuits to conduct an experiment in the classroom, just so you can get an idea of what this kind of project would look like in practice. Now, the next thing I would do is have students design their own circuits based on what they've learned from conducting the modular circuit experiments. Here, students would need to figure out how to combine and consolidate all of these modular circuits to create a new circuit design. And this would require them to design, build, and test their own ideas. Now, in this example, we have a circuit that could be used as a flashlight. And this one design uses two different switches in parallel, which allows the operator to use this apparatus in one of two modes. First, the operator could turn the flashlight on indefinitely using an on-off switch, or they can momentarily activate the light using the push switch. So this is an interesting way to use these basic components within a simple parallel circuit to add functionality. And this is what we really want to see from our projects. We don't necessarily want our students just building a project that's been prescribed to them, but have the skills and knowledge necessary to develop their own ideas into something that they can build and test for themselves. Now, moving on to something slightly more complex, you can see that this circuit operates a string of flashing lights, which you could use it as Christmas, Chinese New Year's, or even at a graduation ceremony. Now, this circuit uses the exact same components that were covered in the modular circuit experiment, and all of these components are referenced in the IGCSE physics curriculum as well. However, the design of this astable multi-vibrator circuit is quite advanced, even though it only uses a few simple parts. And here's another example that's related to science, and this circuit is a water level sensor. As the popsicle stick is placed into the water, the corresponding lights, green, yellow, and red, will light up as the water level raises relative to the sensor. And this type of circuit could be used as a rain gauge for a weather experiment. And my last example before moving on is a circuit design that has been made to control the safety light systems of this model airplane. And these are all circuit designs that only use a select few electrical components that are typically covered in most high school curriculums. However, while most national curriculums that I've reviewed do cover some elements of electronics, they typically only approach electronics from a theoretical standpoint. However, all of these examples just use LED lights, resistors, capacitors, and transistors. There's nothing overly complex or fancy being used in these examples, such as integrated circuits. But even with limited materials, you can see that we're still able to create numerous projects that address real-world needs. And that is really what STEM is all about. How can we use science, technology, engineering, and mathematics to solve real-world problems? And that brings me to another idea of how we can provide students scaffolded learning opportunities to help our students attempt more complex concepts. So these circuits are also modular in nature, but they're standalone circuits as well. And these three circuit examples are actually from the computer engineering course that we're currently working on translating. However, the combination of these circuits shows how different components of an ATX power supply, which can be found in any desktop computer, works. In these projects, students would learn the theory of numerous practical experiments and will use those experiments to validate theory. However, each project in itself is a component of a much larger whole. Therefore, by the end of these projects, students will have completed numerous circuit experiments that would interconnect with one another to create a much more complicated system, just like a real computer does with a motherboard, video card, etc. Now, in this example, you can see a simple fuse circuit to the left. And this circuit is a simple project to help students learn how to build a circuit if they've never built one before. Next is a full wave rectifier, which converts AC, or alternating current, to direct current. And this circuit is critical to computer engineering, but it's also a core element of the IGCSE physics curriculum as well. Finally, the third component is a power stabilizer, which provides the computer with the correct current and voltage for the various components that the various components of the computer need to operate. While the physical structure of an ATX power supply is slightly more complicated than these examples, the core theory of how and why it operates is actually exactly the same. And this idea of computer engineering interests you? Well, you'll be happy to know that we will have another webinar titled Computer Engineering, Reimagining the Computer Science Curriculum, which will go into these topics in a lot more depth. So the next thing that I want to talk about is about making cross-curricular connections and how we can go beyond the project itself to make meaningful connections with the learning objectives of the core subject areas, specifically your math and science classes, as these are the main pillars of STEM education. Now, this example has been taken directly out of a physics textbooks, and it's generally what's taught it most of the time, electronics from a theoretical standpoint. But these kinds of learning examples are normally void of any form of experimentation. And when we look at building a practical electrical engineering or STEM program, we really want to start tapping into that theory that the students have already learned. And we do this by making lessons that apply that theory in context by solving real-world problems. So on the next slide, we'll see some examples of different circuit experiments that apply these theories in a practical experiment. Now, the circuit in the middle allows us to look at the change in resistance through a circuit and how that affects voltage. And the other two examples are math puzzles that would require students to solve a system and then check the results by building the circuit and using the appropriate lab equipment to take readings and validate the results. Now, as for curriculum development, I think it's important to think of STEM integration in terms of horizontal alignment, as you've indicated, rather than vertical alignment, which is common in most content areas. Now, I know some people may disagree with me on this idea, but let me explain. I don't think anyone would dispute the fact that STEM is very different than your other core subject areas. So we need to approach it differently than subjects like English, math, or even science. Moreover, there's no standardized framework for STEM, and part of this is due to how broad STEM education is. And to be perfectly honest, there will probably never be a standardized STEM framework, as programs will vary significantly from school to school based on facilities, teacher expertise, local market demands, and the available budgets that schools have available to them to run said programs. As such, this results in vastly different programs developing at different schools, and in all honesty, this should be the case. So if a school tries to develop vertical alignment in a STEM curriculum when there's no standardized framework, you'll start running into issues. For instance, what happens when students transfer in and out of a particular program? Well, therefore, STEM curriculums really should look at horizontal integration with subjects that do have a relatively universal standard framework. Take math, for example. Every country in the world teaches addition first, followed by subtraction, multiplication, divisions, brackets, and then indices. So if we develop STEM curriculums that utilize what students are learning in their core subject areas and place that theory into context, well, then we can develop specialty STEM programs that are much more feasible for schools to implement. And what I mean by that is that schools can develop STEM programs that apply theory and knowledge in ways that focus on regional market needs while also offering long-term sustainability. For example, programs can be developed within the operational constraints of a particular school, such as the school size, the number of facilities available, teacher expertise, and finances available to run the program, etc. And you can probably see this approach in the previous circuit examples that I've shown already. You don't need years of vertical alignment learning circuitry to jump into any of these projects. Instead, these projects capitalize on years of vertical alignment within the core subject areas while requiring students to apply that theory in meaningful ways with little to no prerequisite skills in development. That means that students can engage with STEM activities at the higher grade levels even if they've just transferred into a new school. And that's where I think we really need to focus on, that's why I think we really need to focus on horizontal alignment in STEM education, so that we can capitalize on years of vertical alignment in the core subject areas such as math and science, rather than trying to look at ways to develop a K through 12 alignment in STEM, which can create a whole slew of other problems, which becomes more difficult to deal with as you get into the higher grade levels. So here I have one more example which shows how horizontal integration with other subjects areas can work. And in this video really shows the students are getting into the physics curriculum, but also the computer science and design technology programs as well, while also developing the students' dictation skills in their second language. Now in this video you'll see that these students are explaining the designs of their own circuits, which are based around computer logic gates. And for reference, all three examples are of an exclusive OR logic gate, but each project has been created using a very different design method. And you'll also probably notice that they're using multiple modular circuits in this experiment as well. So let's take a look at what these students have done, and keep in mind that these are ESL students, so their English may not be perfect. However, they did a great job of explaining complex ideas, especially considering that some of them have only been learning English for 1 or 2 years now.
Let me show you the work. Yes, the XO gate is only A or B
This is my experiment. I want to introduce the tabs. As we can see, we have the two line and the one underground line. So if the power is two, only one power is through here, through the yellow line, and to the resistor, and through to this one is the light, through the light, and the power goes here, and then goes through to here and here, and through to the ground. And another power, if you go, we can go to the orange line, and also need to through the through the resistor and through the light, and go to the ground. But we cannot through the two power together. If the two powers through the line and through the line together, the light will not bright. Let's have the explain. Put the light. 这个线怎么接啊？这样子的吗？这样。So let's read the power A through the yellow line. That's the light will be bright, and the power B through is okay. It's okay. So if the two powers are together, the light will not be bright. That's it. My gate is XOR gate. When the input A is on, the power will go through the yellow line and the light is on. Same as A. If input B is on, the power will go through the orange line and the light is on too. If both inputs are on, the power will go through here and downwards to the ground, so the light is off.
So as you just saw, all of these students built an exclusive OR gate using different approaches. And in this project, they have applied advanced theories in computer science while also integrating numerous theories that they've learned in the physics curriculum as well. And this is also the first time that these students have ever made circuits as well, was in this class. So they started by building a simple fuse circuit like what you saw in the modular ATX power supply project, and then they progressed through a series of different circuit experiments which all interconnected with one another to create a more complex experiment like what you see here. So while it may not have been self-evident as to why I recommended using prototype boards earlier in this presentation, I'm sure you're starting to see the value of it now. But it really comes down to looking ahead and planning for things that we want to undertake in the future, while also planning a logical sequence in the work that will help us achieve that outcome. And that's the premise of backwards design in curriculum planning. And with that being said, our next topic is the introduction of computer-aided design. So let's take a look at how we can help our students transition from physical circuits to creating more advanced computerized simulations. So here we have a 10-year-old student, and normally I wouldn't recommend trying to teach these kinds of concepts and skills to a child of this age. However, I've been tutoring the student for a number of years, and his mother really wanted some challenging projects for him to undertake during the initial COVID lockdown. So here you can see some photos that his mother took of him while he was making this USB cell phone charger in their kitchen. And she was immensely proud of her son and what he had done. And so she made this post saying that one day her son would go on to become an electrical engineer. And this is actually one of the most popular projects that I've designed over the years. Now there's several different leveled project designs available, making it much easier for teachers to provide differentiation when using this project. So you do have variations of the same project so that all students will be able to achieve the same desired learning outcomes while also having the ability to select a design that suits their particular skill level. And if you're interested in what people think about this project, here are some of the comments that have been made by different educators about this project in the past. And this is just one of hundreds of circuit projects that tie into different aspects of the curriculum that we've developed. Now I've already shown these two images before, but here we have a breadboard to the left and a prototype board to the right. Now I'd like you to think about which one of these designs would be easier for a student to recreate using a CAD program and why this would be. So I'll give you a moment to think about your response, and maybe you can share your thoughts as well. Now, as for electronics, we use specialized CAD or computer-aided design programs that are specifically designed for electronics. Because after all, electronics is a unique area of specialization, so we do need to use a CAD program that can support our specific needs. So a lot of educators that I've talked to have asked me why I hardly use breadboards when teaching high school students electronics and electrical engineering. And as I illustrated earlier in this presentation, breadboards require students to make a lot of abstract connections, which only complicates things for someone learning circuitry for the first time. However, there's another more important reason why I opt out and focus on the use of prototype boards instead. And this is because developing a STEM curriculum is kind of like playing a game of chess. You need to think 5 or 6 moves ahead. And that's the reason why I've taken the time to have the students develop circuits using prototype boards instead of breadboards. Because I'm thinking about what I want to accomplish and what do I need to do now to make future learning outcomes easier for my students to acquire down the line. So as you can see in this example, the layout of the prototype board is identical to what it looks like if you design the circuit using a CAD program. And this is, in essence, makes it incredibly easy for students to transition from a physical circuit design to a computer design in a matter of moments. And finally, the use of the prototype board also results in students creating a low-cost project that they can take home and show their parents and potentially keep for years to come. Now again, this is a 10-year-old student learning how to use a CAD program to recreate the circuit on the computer. He is referencing his original circuit in order to recreate it on the computer. Now he's never used a CAD program before. This is the very first time designing something on the computer. And you can see that in a matter of minutes, he's already designing something using a professional grade CAD program. So there you can see his original circuit on the keyboard, and he's looking at his circuit and then recreating it in the CAD program. Now, if you're interested in some recommendations, this program is called iCircuit, which is an incredibly powerful program that only costs a few dollars to buy online. But you can also use circuitlab.com as well, which is another great low-cost option. And this idea can lead into other ideas as well. Now, I like to use this circuit when teaching students how to design a circuit on the computer, as it's the easiest astable multivibrator that you can make. Now, for reference, this kind of circuit is what you would use to create the flashing lights for a railroad crossing or a school bus. So I would have the students build and test the circuit and then recreate it in a CAD program. And because the lights will oscillate automatically, it makes it a great circuit to simulate on the computer. Now, compare the physical model to what the circuit looks like on a computer simulation. Now, in this computer simulation, you can see the layout and the placement of the parts and wires and the components is exactly the same as the physical model. The only difference is that we're using symbols to represent each component. And we can even predict how the circuit will work in the CAD program when we play the circuit simulation. So this is how I introduce CAD to my students for the first time. I have them start by building a physical circuit and then use that circuit as a guide to recreate it using the computer. So here we have another student project, and again, I had the student, this student had never used CAD, a CAD program in their life before attempting this project. Now this project was done in Circuit Lab, which you can use for free for this kind of activity. So you don't need to spend lots of money to do this kind of project with your students. And another thing that I like is to have the students record their work so that I can see every mistake that they made and what they did to fix the problem on their own. And I think this process of self-revision is incredibly important for both teaching and learning. Now this project is about 1 hour to do, and of course the students have sped up the recording. But that means that in just 1 minute, I can see the student's entire learning process from start to finish, which provides me with an excellent tool to provide both formative and summative assessment. So high-quality projects that link into the core curriculum are key to reinforcing and strengthening a student's understanding. By providing students with examples of how theory can be used in real-life contexts, students are empowered with the foresight that they need to understand where their education can lead them in the future, thus helping students pursue a path of lifelong learning. And in a moment, I'll model what this could look like, so that I can give you an idea of how theory can be applied to projects that demonstrate the real-life application of theory and theoretical science. Because at the end of the day, we don't want these concepts to remain as abstract ideas. We want to look at ways that they can reinforce the core curriculum by placing it into an appropriate context that makes it relevant. So at this point, I'm going to model a lesson for you so that you can see how projects and theory can be intertwined. In this example, I'm going to look at how we can convert wind energy into electricity using a rectifier circuit. In this example, we cover ideas from a number of different courses such as social studies, geography, physics, science, design technology, and electronics. So there's so many different connections that can be made in a project like this. So let's take a look at how we can use a guided inquiry-based learning model to help students develop a deeper understanding of core theories and how those theories can be applied to the context to solve a real-world problem. So we definitely need to start by building foundations, and that's what I'm going to start with right here. Now we need a wind turbine. Our wind turbine to output a stable 5-volt output. And a 5-volt direct current would look like this, basically a straight line over time. But a wind turbine uses an alternator to produce power that creates an alternating current. But an alternating current, or AC, starts at 0 volts. It then increases to its maximum positive amplitude, and then starts decreasing to reach its minimum negative amplitude before returning to a value of 0 volts again. So what would this look like if we graphed this using the same template as before? Now give your students a moment to think about the answers before showing it to them. So a 5-volt alternating current would look like this. It's actually a sinusoidal function for those of you who teach grade 11 math. But essentially, this is what we get from an electrical turbine. And we also have a number of vocabulary terms here that we should introduce to the students so that they understand how to properly describe a sine wave. These terms include the crest, which is the maximum positive amplitude, the trough, which is the minimum negative amplitude, the wavelength, which is the distance from one crest to the next, and we have the amplitude of the wave, which is basically the measurement from the midpoint to the highest and lowest points in the waveform. And these are all terms that are important to review in the physics curriculum, but they also get used in music as well. So what we essentially need to do at this time is to build a circuit that solves this problem for us. That is to change an alternating current such as this to a direct current like this. So these are all common electrical symbols that you'll find in the physics and design technology curriculums. So we have a diode, capacitor, resistor, PNP transistor, ground, and an NPN transistor. So rather than giving my students the answers, I would give them, or at least guide them towards discovering the answers for themselves. Now before I move on, what component do you think we could use? And what evidence do you have to support your answer? Again, our objective here is to find a way to convert an alternating current to a direct current, and one of these components has the ability to do that for us. Now, if you don't know what the answer is, don't worry. The main idea here is to help give your students the opportunity to develop ideas and to try to support those ideas with evidence, which really helps getting a two-way dialogue occurring in your classes. Now, the correct answer to this question is a diode, and the reason for that is that it only allows power to flow through it in one direction. So by using a diode, we can limit the direction that the power flows in a circuit to one direction only, and this will eliminate the negative duty cycle of an alternating power source. So to put it another way, only the positive part of the duty cycle, that is the part of the sine wave that's above 0 volts, will be allowed to flow through the circuit. And as a teacher, I recommend that you try phrasing things in several different ways to really emphasize some of those key ideas. And this is because repetition is incredibly helpful to students as they try to remember new concepts. Therefore, rephrasing and repeating the same idea more than once will help give your students more opportunities to absorb those big ideas. Now, I would like to give you a task. What do you think a 5-volt alternating current would look like if a diode was inserted into the circuit? Again, give your students a moment to try to come up with a solution on their own. Now, as a teacher, you could have your students draw the graph in their notebook, provide them with handouts, or you could even ask them everyone in the class to draw the graph using their finger in the air. Then, as a teacher, I could instantly see how many of the students were able to predict the results accurately, which is a quick and easy way to perform a quick assessment for learning in the middle of a lesson. And the correct solution is this. So this is the output of a half-wave rectifier. Now, we still have the positive duty cycle, and the negative duty cycle has essentially been eliminated by the diode. So what would this look like in a computer simulation? So in this short animation, we have an alternating power source that I've set to 1 Hertz so that we can see what's happening with the electrons. Next, we have a transformer, which basically reduces the 240 volt power supply down to 12 volts for our classroom projects. And this is really so we're working with a low voltage power supply, which is much safer for our students to use. So in this circuit, we have power coming from the transformer through a single diode, then through a light before returning to the transformer. All right, now that we understand the layout of the circuit design, let's run the simulations to see what happens. So you can see the yellow electron flowing through the circuit. And basically what's happening is the LED light is flashing once every second. Now, this circuit is known as a half-wave rectifier and is a topic that is covered in the IGCSE physics curriculum. So what's wrong with this half-wave rectifier? Well, we don't really want the lights in our house flashing or the power to our TV turning on and off automatically. It's evident that this circuit really isn't a viable solution to our problem. What we want is to take an alternating current from our wind turbine and to convert it into a stable and reliable power source. So what we have right now is just part of a solution, but we don't have a complete solution yet. Therefore, we need to redefine our project. And this is a big part of STEM education, coming up with an idea, testing a hypothesis, and then evaluating the effectiveness of our design. Then we find ways to improve upon our original concept so that we can continually advance our designs. And this is exactly what engineers do in the real world: design, test, and rebuild. So the problem with the half-wave rectifier is that power is only supplied to the load when the power cycle is positive. That is, when the part of the sine wave is above 0 volts. And this means that the power is being turned on and off at regular intervals, which results in the light flashing. Now, to fix this problem, we need a specialized circuit that's known as a full-wave rectifier. And again, this is a concept that's covered in the physics curriculum. But a full-wave rectifier is a fair bit more complicated. So this circuit diagram is for a full-wave rectifier. It kind of looks like a traffic circle, and it essentially works in the same way. And that's because the electrons can only flow in one direction, just like cars can only drive in one direction when they enter the traffic circle. So this circuit basically results in the electrons flowing through the circuit in the same direction. Now, what did you notice about the LED light? So you might have noticed that the LED light is still flashing, but the time that the LED light is off is much shorter than it was before. And this is because there's now 2 paths for the electricity to flow in order to get to the main circuit loop. And this means that when the power cycle is positive, the electricity will flow through the full wave rectifier in one direction, and when the power cycle is negative, the electricity will flow through the full wave rectifier in the opposite direction. So in other words, the negative part of the sine wave will be inverted, but there's still a rising and falling action occurring in the supply of power. So I'd like you to take a moment to think about how you would graph this. So again, using that same graph template that was used earlier, try to graph the revised sinusoidal function and what it should look like. Now give your students a chance to do this task on their own before showing them the correct answer. Now this is what the final waveform would look like. We have an inverted, we've inverted the negative part of the duty cycle, which makes it positive. However, we still have a rising and falling action. And as you can see, there are momentary points in which the power drops to 0 volts. And that's why the LED was still flashing. So there is a way to fix this problem, and it's not overly difficult. Essentially, all we need to do is add a capacitor to the circuit in parallel to the load. Otherwise, the circuit is exactly the same as before. So what do you predict will happen when we add a capacitor to the full wave rectifier circuit? And I would also like you to try to justify your answer with any evidence if possible. Now hopefully you have an idea of what's going to happen, but if you're not sure, don't worry, because we're going to watch a simulation of the circuit together. So right now you can see the flow of electrons through the circuit, and we have the values entering and exiting the capacitor changing rapidly. And this is because the capacitor is charging and discharging as the potential difference in the circuit changes. So a capacitor is kind of like a battery. When the power cycle is high, the capacitor will start charging and storing power. And when the power cycle is low, the capacitor will start discharging that power. And this releases power back to the rest of the circuit. Therefore, that capacitor is providing power to the LED when the power drops down to 0 volts. Now, I really want you to analyze everything that's happening in the circuit before we move on. And there's still moments where there's no electrons flowing through the full wave rectifier. However, the LED light still remains on at all times. And this is because that capacitor is powering the rest of that circuit during those moments that the flow of electrons is changing direction before entering the rectifier. So we finally have a usable circuit that we can use to in the design of our wind turbines. And once more, I'd like you to try to graph the final output of the circuit, and this will be our last graphing activity before moving on. Now you might have drawn a straight line. However, the correct answer should look like this. There will still be minuscule fluctuations in power as the capacitor charges and discharges. However, these fluctuations will be so small that the average electronic device will not be affected by these changes, as these variations in power will be within the acceptable tolerance range. Therefore, in practice, we have a usable power source at this time. Now, put into practice or into a practical project, here we have an oscilloscope which is used to analyze waveforms and a series of circuit board projects. The first image is basically the oscilloscope plugged into an alternating power supply, followed by an experiment that allows us to do a comparative analysis between a half wave and full wave rectifier. And finally, the third image shows a full wave rectifier with a high capacity capacitor, which has given us a perfect DC output. So in these examples, you can see that we are no longer just looking at things from a theoretical standpoint, but are actually applying core theories in context to solve real-world problems. So if we look at these types of horizontal integration with these kinds of STEM projects, we can see that a single project can address a large number of learning outcomes. For instance, these are all aspects of the IGCSE physics curriculum that would be covered by this one project. Now here's one of the project sheets that you can download from SinoExchange that shows you how to build these kinds of circuits. This particular example is for a 3-phase rectifier, which we haven't actually covered yet. However, in this circuit, we're rectifying 3 different sinusoidal functions that are offset by a phase shift of 120 degrees each. And this provides us with an even better power output, which is evident by the data provided in the accompanying graphs. But as you can see, this one project is able to target so many different learning standards, and these are just the standards from the physics curriculum alone. And then you can start thinking about environmental sustainability and social impact standards from the human geography curriculum. And so we have a project that might tie into every single subject that the student is taking in a given year. Moreover, this project is just one of many projects that we've designed around sustainable energy solutions and smart home technologies. So I'm going to show you another student video from a group of 3 girls. And this actually brings me to another idea. What can we do as educators to encourage and support more girls to pursue a career in STEM education? So in this video, we saw these 3 girls making circuits that could be used in a variety of smart home applications. The first circuit is similar to what you see in the LED lights, which allows you to toggle between a high and low setting or a warm and cool color temperature. The second was a home security alarm that would beep if someone enters the room or if a window was open. And finally, the third circuit was a fire alarm. And we have templates that you can download to build these circuits for yourselves. But because these are all based on the use of prototype boards, you can customize any of these circuits. And this allows you to simplify projects or even add additional layers of complexity. And this provides your students with scaffolded support, which will help them excel while also providing methods for differentiation at the same time. So at this point, you're probably wondering, what do you need to get started? Or that you might be thinking that this is going to be super expensive. But in reality, it's not. After all those videos, you probably haven't seen many tools. So right now, we'll take a look at some of the tools and equipment that you need to get your own program off the ground. So you definitely need the following 3 tools. Now, I don't recommend buying toolkits because you tend to get a lot of things that you don't need. And the quality of these tools and pre-made kits are usually not that great either. So I recommend buying just the tools that you need, and having fewer tools also makes it easier for your students to learn what to use, when to use it, and how to use it properly. So starting from the left, you'll need a pair of 45-degree pliers that are designed for cutting wires. Next, you'll need a 20 to 30 gauge wire strippers. And finally, 45-degree precision tweezers. And these tools are not overly expensive. For instance, the most expensive item there is the wire strippers, and these only cost about $12 US or 100 RMB if you're buying them here in China. Next, you'll need some soldering irons, and there's a few different types that you can buy. The higher end unit on the left has adjustable temperature controls and replaceable tips, which are incredibly useful. The small USB soldering iron on the right is another great choice for schools and electronic programs, and I really like this type of soldering iron for a few reasons. First, they do not get overly hot, which reduces the chances that students will damage sensitive IC chips by overheating them. Next, they can draw power from a student's computer or from a portable battery pack, and this can reduce how many wires and extension cords you need to use during your lessons. And finally, they're incredibly inexpensive, so I often give them as consumable items to my students, giving every student their own soldering iron at the start of the term, which they're then responsible for the rest of the year. And then the one in the middle, which is typically what most people would instinctively buy. Regrettably, these are the worst possible soldering irons that you can buy for educational purposes. They have a large tip which is not suitable for precision electronics. They get far too hot and can damage your components, and due to the high temperatures, the tips quickly oxidize, and that makes it more difficult for your students to use. So my recommendation is don't buy this type of soldering iron because they're not designed for microcircuitry. They're designed for high voltage industrial applications, which your students will not be doing in class. The next set of items you'll need to keep things organized will also addressing safety concerns. The first item is an inexpensive desk organizer from Delhi. And I really like this particular item as it's the perfect size for holding tools in the back section, a roll of wire and solder in the front, and the helping hand units where you see the notepads. Therefore, you can you can have a completely self-contained kit, which you can store in a locker with everything a student needs to build their own circuits. Then students can easily grab a complete kit at the start of class, and then return that kit at the end of class, making it easy for the teacher to manage everything that's going on. The next item is a blue soldering mat. Now this is a heat-resistant silicone mat, and a simple A4 sized mat is sufficient. These mats do not conduct electricity, have places to store loose parts while you're working on your circuit, and can withstand prolonged exposure to heat from a soldering iron. These mats are not expensive, and they will protect your workspaces. They can even help prevent a fire if a student forgets to unplug a soldering iron, which is something that can easily happen during a fire drill or lockdown. So I'm not sure why a lot of schools don't buy these kind of safety mats, because they're not expensive and they can make a huge difference. And finally, we have helping hands. These are a must item. Helping hands hold your circuit boards while you're working on them, and this keeps your hands away from the hot end of the soldering iron, which can reduce your chances of getting burned. So you only really need 4 tools: a safety mat, a desk organizer, and this is all you really need to start an electrical engineering program at your school. The last item that you might want to get is a good multi-purpose meter, and this will become an important tool when you start taking readings and analyzing data from your experiments. However, there are so many options on the market, so it can be hard to choose a good meter for your program. So here I'm showing 2 different models that look very similar, while being very different at the same time. Now, I'd like you to take a moment to think about which one of these meters you would buy for your school and why. Which one do you think is better? And which one is more advanced? Well, not all multimeters are made equal, and looks can be deceiving. The one on the right is what a lot of people would indicate that they would buy, and is also what I've seen in most schools as well. It looks more advanced. After all, it has more settings. But in my opinion, this is one of the worst types of meters that you can buy for education. And this is because looks can be deceiving. With this kind of meter, you need to know exactly what values you're expecting to test and manually set the range on the meter. And as a teacher, you'll likely tell your students to set your meter to a particular setting. But your students will ask why, and you'll likely respond, just because that's the setting we need to use. However, if I already know the values that I'm expecting from the test, then I wouldn't be testing the values in the first place. Moreover, if the meter is set wrong, the consequences can be deadly. For instance, I might have the meter set to a low voltage range while testing a high voltage wire. As a result, the meter will often show 0 volts because the actual value is out of range. And this can result in a student misassessing the situation and working on a live circuit. Therefore, these meters are particularly bad for education because they're overly complicated, making it difficult for the students to use independently. And the lack of auto ranging can result in avoidable mistakes, which could lead to either injury or even death. However, the meter on the left is actually a far superior model and is used by industry professionals. While this meter looks simple, it's actually state-of-the-art auto-ranging meter. This means that the meter is sophisticated enough to identify the appropriate range of what's being tested and set the scale accordingly to provide the operator with precise results. As a result, this meter will be significantly easier for students to learn how to use, while also being much safer. Moreover, professional brands like Fluke will provide many years of reliable service, making the investment worthwhile. Now, I've used numerous meters over the years, and most of them don't even last the year. However, I've never had to replace a Fluke meter in more than 10 years of teaching electronics. So although they're a little expensive, they're absolutely worth the investment. Now, as I mentioned earlier in the presentation, do-it-yourself kits become very costly and tend to lack any associated methodology that would help students develop a deeper understanding as to how or why the circuit works. Therefore, the use of prototype boards provides a superior solution for educators. However, this means that educators need to develop circuit designs that are aligned to a core curriculum while also reasonable enough to expect students to attempt on their own. Typically, this has been a limiting factor that has made the development of practical and cost-effective electrical engineering programs a fantasy for most schools. However, that's about to change. SinoExchange has already released over 100 circuit experiments to the general public, all of which have been made available completely free of charge. Moreover, we have designed all of our projects to use the fewest number of base components to make it easier for you to maintain an inventory of key electrical components. And this also allows you to buy in bulk so that you can keep your costs down. However, since we are a charitable organization, we do not sell any education kits ourselves, but we have provided you with links to third-party suppliers to help you get started. And as you can see, this example, 22 RMB, that's about $3 American for 1,000 LED lights. So you can start thinking about how cheap these projects actually be in reality once you actually have all the parts you need. Now, if you're interested in getting started, you can always go to sinoexchange.com and under resources, there's a whole section on electrical circuit design. And from there, you can find a whole bunch of different projects that you can download and use completely free of charge. So we've created a completely free and open platform. There's no subscriptions, no user fees, and no unwanted ads. What we've created is a platform that's truly accessible to anyone, regardless of their social or economic background. And this means that anyone can access educational resources to learn about a topic that may interest them and embrace a journey of lifelong learning. Now, if you found this webinar enlightening, you may want to consider attending any of these other upcoming webinars that are related to the development of high-quality STEM programs. All of these presentations are equally as informative as this one and will provide you with evidence-based examples and project modeling that will help you design your own STEM programs that will help prepare your students for the new global economy. These webinars include why there's no future in STEM and what we can do to fix the problem, developing a sustainable STEM program and how to create cost-effective programs that focus on developing core learning outcomes rather than a dependency on technology, computer engineering, reimagining the computer science curriculum, and computational algorithms, a visual exploration for non-programmers. So that brings us to the end of this presentation. So I'd like to thank you for attending this presentation of electrical engineering, establishing a practical engineering program without breaking the bank. I hope you found this presentation informative, and I implore you to consider attending our future webinars.